In a previous video, we discussed the concepts of stress, strain, and Young's modulus. And here I've defined again stress and strain. At the top of the screen, you see that stress, which is the Greek letter sigma, is equal to P divided by A. P stands for load or force, and A stands for cross-sectional area. Previously, I had used an F. I'm now making the switch from F to P, as well as in the strain equation switching from X to lowercase delta to mimic what you are likely to see in most textbooks. So these two definitions are the same as we've seen before. Stress is force or a load over a cross-sectional area. If we want to define that in terms of our photograph down here, we have a material in a testing machine. By the way, the material is often called, in a generic way, a dog bone based on its shape. It gets a little bit bigger here at the top, a little bit bigger at the bottom, and in the middle it is a uniform cross-section. And it's often called a dog bone, so you'll hear people say, I need you to make me or get me a dog bone to test. So here we would have, say, a force upward of P and downward of P. And if the dog bone was cylindrical, the area of this cross section would be pi r squared, the area of a circle. And strain, which is represented by the Greek letter epsilon, is equal to delta over L, where delta is the amount by which the material stretches and L is its original length. So if in this picture we define the original length as the distance between these two clamps, this is L, sometimes people put a subscript 0, and delta would be the amount by which it increases. So if we look in this second picture where the object has been stretched a little bit, we can compare the two pictures and find the difference in length. And maybe the difference in length, if this is L on this picture might be an equivalent like right here. These two sections should be the same, and then the additional little distance right here is delta. Okay, so think of it this way. An object will strain under a given stress, and the more you stress it, the more it strains. Strain is a measure of stretch. Strain has no units because it is basically given to us as a percentage. If strain is 0.02, then the object has a 2% stretch. Stress is often given in pounds per square inch, but it's sometimes given in other units. Okay, so now that we've had that little bit of review, let's write the equation we learned last time. Stress equals Young's modulus times strain. That is, you can think of this new quantity, Young's modulus, often called the modulus of elasticity, as being a number that is equal to the ratio of stress over strain. And this only makes sense when this ratio is fixed. Probably makes more sense to think of it this way. Change in stress over change in strain. Okay, so if my stress goes from 50 psi to 100 psi, and my strain goes from 0.005 to 0.01, for instance, I could divide those two quantities and obtain my E. And for any other change in stress, I would obtain a change in strain that gave the same ratio. When you write it this way, and based on what we saw last time as well, that this is of the form y equals mx, it becomes apparent that E is a reference to the slope of the graph that you obtain when you graph stress against strain. Just like m represents the slope in the equation y equals mx, the standard equation for a line, e represents the slope, the rise over run, in a graph of stress versus strain. And the steepness of this slope, that is Young's modulus, is an indication of how stiff a material is. So a material that is very stiff will have a very steep slope. You apply a lot of force and it stretches very little. And a material that has a very small slope would be flexible, and you pull it just a little bit and it stretches a lot, kind of like rubber, or exactly like rubber. Okay. As a reminder, materials must obey Hooke's law if their graph is to look like this. And there are materials that do not obey Hooke's law, where their graphs are not linear. So you should not expect every material to have a linear graph. Materials that do have a linear graph are obeying Hooke's law. And this equation, which is basically a form of Hooke's law, is valid for those materials. Now, in actuality, most materials only obey Hooke's law up to a point, up to some maximum stress. And at any stress beyond some specific value, they stop obeying Hooke's law and their graphs no longer look linear. Let's see an example of that. Okay, so now I've placed a graph on the screen. We can see here that this material is obeying Hooke's law up to this stress right here. And at higher stresses, the material is no longer obeying Hooke's law. That is, once we're above this line, if I double the stress, then the strain will not double. If I increase the stress 3%, the strain will not increase by 3%. It will increase by more than 3%, actually. At this point, small increases in stress result in larger strains than we are accustomed to seeing. The object really starts to pull apart. It pulls apart, and right here at this highest point, something begins, and you can see right here that something is called necking. The material starts to decrease in cross-sectional area. As we see here, this is what necking looks like. It becomes narrower like a neck. Okay. And then the material continues to pull apart at this location. It won't neck more than once. We won't find a neck elsewhere. Basically, a weak point is identified within the material. The material is pulled apart at a weak point, and it fractures at that point. So the fracture, which we see right here on the graph, where the graph ends, of course, corresponds to the point where the material has now broken, and we're no longer collecting any data. Now, let's look at how this graph is labeled. We're reminded that the slope of this line is Young's modulus. Okay, it says rise over run. It's also stress over strain, obviously. This point right here is labeled as yield strength, and you will also sometimes see it labeled as yield point. So we should be prepared for either yield strength or yield point. The corresponding stress would be the stress at your yield point. Okay, that is the letter sigma with the subscript YP for yield point. The maximum stress that the material withstands prior to breaking is right here, and on the y-axis right up here, and it is referred to as the ultimate strength or ultimate tensile strength. So we might label it stress UTS, ultimate tensile strength. So what does the word tensile mean? Well, there's two ways that we could apply a force or a load to a dog bone. We could pull it apart, pulling outward on both sides like I've already depicted here, where there's a load pulling outward, or we could push inward. Tensile refers to pulling outward. That is, the object is in tension, just like a rope is in tension or is tense when you pull on both sides. The opposite of a tensile force is a compression force. There are machines, basically the same machine but set up in a different way, can apply a compression force and push inward on both ends of a material. As you might imagine, most materials can handle more compression forces than they can tensile or tension forces. Okay, so this is a measure of the ultimate force pulling outward, the ultimate tension or tensile force. I'll mention something that we won't worry too much about. I just want you to know that it exists. In the necking section of the graph, stress is calculated using not this smaller cross-sectional area, but the original cross-sectional area. That is, we don't change the value of A as we determine the stress at this point. The machine that is calculating this data force and plotting it for us on a computer is measuring the load or the force. It's not measuring the cross-sectional area. You actually type that into the computer. Okay, and you type in what it starts out as, and the computer uses that value in calculating stress. So it's not going to know that the material is necking, and it's not going to change the value of A. Okay, so actually we use an artificially high value for A in this region. And if we were to use the actual value of A, this graph would look different. It would actually curve upward. We're not going to worry about this, and we are going to continue using the original value of A, the value that you would actually find given to you on a machine if you were to test this in a lab somewhere. Okay, let's move on. So let's say you take a dog bone, perhaps of aluminum, and you apply a small stress, maybe up to this point right here, and the object will strain a bit. So we apply stress 1, and the object stretches a bit, corresponding to some strain, which we label strain 1. What would happen if you then removed the load? And it turns out that the object will return to its original size as long as the stress was below the yield point. As long as the stress is below the yield point, you are somewhere here. That is, the object is obeying Hooke's law. When you remove the load or the force, the object returns back to its original length and exhibits zero strain. We call this property elasticity, and we say that the material is behaving elastically. What do we call it when the material is not behaving elastically? That is, up in this higher portion of the graph, where we are beyond the yield point. The term is plastic. The object is behaving plastically. We say at this point it is deforming plastically. Now that does not indicate the object is made of plastic. To say something is deforming plastically simply means that if you're applying a stress and you remove that stress, the object does not return to its original length. It might shrink back a little bit, but it will not return to its original length. Okay? So for most materials, they will deform elastically for a while, and then beyond some point, they will deform plastically. A few materials will break before they ever start to deform plastically. That is, they are elastic up to the end, up to the fracture point, And for those materials, there is no curved portion of their graph. The graph is completely linear the entire time. An example is glass. It might seem difficult to believe that if you pulled on glass it would stretch, but it actually does. It stretches a little bit. It stretches until pop, it breaks. Sometimes people are interested in the stress associated with the break point. And that's simply the stress or the Y value associated with this point labeled fracture. So you could read that off of your graph, or more likely the computer connected to the machine will print out this value for you and you'll read it right off the screen. Okay, let's put some numbers to some of these concepts. Let's examine the ultimate tensile strength for a few common materials. Muscle tissue has an ultimate strength of only 15 pounds per square inch. Concrete has one of 600 pounds per square inch, which is actually rather small, which is why concrete is typically reinforced with steel bars. Skin has an ultimate strength of 1500 psi, 100 times that of muscle tissue. It's much more difficult to pull skin apart than muscle tissue, but let's not think of either. Ordinary glass can range from 5,000 to 25,000 psi. Tendon, which binds muscle to bone, has a rather large ultimate strength of 12,000 psi. Copper, pure copper, has an ultimate strength of 20,000 psi. Mild steel, 60,000 psi. Most structures that are made of steel are made of mild steel. It accounts for most construction. And then occasionally we find high tensile steel used in certain situations, typically when the project is rather small or the object is rather small. High tensile steel has a very high ultimate strength. The drawback is that it's costly and that cracks propagate more easily than they do in mild steel. Nevertheless, it does have a very high ultimate strength. It takes a lot of tensile strength to pull apart high tensile steel.